engineering AI systems. And I hope the discussion will be very interactive. So if you have questions, even during the talks, if IPEC can handle this, just shoot the question. I'll be happy to take them and then discuss as we progress. So this is the standard slide. I think there is no news here on this slide for anyone. Machine learning, it's making inroads in products. So we passed the level of training algorithm for specific tasks. We're now deploying machine learning components and systems. We are mostly already using some of those in our daily activities. And it's even been deployed in safety critical domains, which makes the reliability and trustworthiness of those systems very, very critical. So what I do with my research team at Montreal, it's really trying to focus on the top of this iceberg, trying to make sure that we can build reliable software systems. And if you look at the full picture, you can see that this encompasses a lot of challenges that are hidden underneath, right? So contrary to traditional systems, machine learning-based systems are heavily data-driven, which means we have additionally to care about the quality of data. Every issue in the data usually translates into the models. So the modeling phase is also very error-prone. Very often, we have to deal with under-specified models, so we have to ensure that we're doing this optimization right so that we're getting the better artifact out of the process. And even once this is done, we still need to instruct the computer to provide the result out of this. So we need to write the code, and the code can be buggy. So there is a lot of issues that need to be handled if we want to implement reliable machine learning systems. And this is a continuous cycles, right? So we build, and then the system evolving. We have to keep monitoring for this and maintaining quality of the systems going forward throughout the life cycle of the system. So to build a trustworthy AI system, there is already a consensus that is emerging that we need to do more than just building accurate algorithms, right, in the model. We need to ensure that this component, the AI component, are explainable. We're having many regulations coming every day to ensure that whenever this technology is included in the product to provide services, we need to be able to explain the rationale behind the decisions that the AI components are doing. So explainability is something that is becoming prime in the engineering of machine learning-based systems. Fairness is another problem it's already well known. We have been seeing headlines about products that have been designed using machine learning components that often make decisions that not necessarily ensure a fair treatment to all the users of the service. The privacy is also a very big problem that has to be maintained because this is heavily data-driven. These data are assets that contain information that often should not be leaked or distributed without consent. So ensuring the privacy of the information that is used to build the systems, it's a challenge that the community is also tackling. Robustness and causality, it's another aspect. So recently, we have seen the past 6 months with ChatGPT doing the headlines. We're having the models that is able of displaying sometimes very impressive capability, but also sometimes very failing on very simple tasks, right? And one reason behind this is also a lack of reasoning behind the technology. And there is a strong belief that causality probably could help a bit on this. So there is a push in that direction as well. And the model, the component need to be robust to ensure that the system, when it's deployed in the environments, can still maintain a decent level of quality level of services despite all the changes in the environment. So these are challenges. So if we briefly go through some of these challenges, we'll see the type of machine learning model that is providing the services that are the most advanced today are often black box. So explainability and interpretability it's a big challenge. There are techniques that are proposed and explored, but unfortunately they still don't work well. So if you just look at this example, we have on one side a well-trained model, and on the other side an untrained model, which is actually poorly performing. But if you look at the science map, they often look quite similar. So this medium for assessing the explainability of the model, it's not a reliable tool. Another very popular example that's have been in the headlines, it's this case of a model predicting a Siberian husky and a traverse fluid just by activating similar patterns of neurons. So this attention maps, although in some cases, they seems to provide a hint where the model is looking at when making the decision. It's still not a very reliable tool in terms of explainability. So explainability for this model is still a very big challenge. Even more troublesome is the post hoc explanation techniques that's are gaining in popularity, including the software engineering community, where we try to build more smaller interpretable model to mimic the behavior of the black box model and use that small model to try to explain what the black box model is doing. Turn out they are not reliable, right? So in a recent study, I think we published this 2 years ago, we experiment with different post hoc explanation techniques. And what you can see is that they really often disagree on how they think the model is getting to the decision. So explainability is still very, very challenging. And even more troublesome, this year we have another work where we actually show that you can actually manipulate this explanation. Right? So it's in this example, we show that you can hide the contribution of a sensitive attribute just by playing with the sampling that is used to generate the post-hoc explanations. So in this case, the model is making decisions based on the gender, but by sampling in a specific way, we can actually generate explanation that's hiding the fact that the model is basing the decision mostly on the gender attribute. So these techniques are not reliable, and we still need to work to build more robust techniques for explainability. Another challenge for trustworthiness is the issue of biases, right? So there are techniques that have been proposed to try to mitigate biases in the data during the training process, after the model is being trained, but it's still something that is challenging, and we are not there yet in terms of bias-free models construction. Another challenge for trustworthiness is the robustness. We all have seen this example, where just slight perturbation of an image can actually significantly alter the decision of a model. So the models, their works usually reasonable when they are in distributions, but whenever we go out of distribution, this model tend to fail very brutally. So it's very important to understand the operational envelope of this component to be able to use the model only within the context in which they can be trustworthy. So robustness it's a big challenge when we build a system. So at this point, I guess if you may be asking, well, where is the place of trustworthiness here, right? Like, can we really build a trustworthy system with unreliable components? Right? I guess this is why we're having this community at CAIN to try to come up with engineering techniques and tools that can allow us to kind of achieve this goal. My perspective is that in a system view, although the individual component may have different latent failures, if we build a very good understanding of how the components are failing and when they are working properly, we can stitch together to build a robust system. Right? A bit like this analogy with the Swiss cheese. So the work that we're doing is mostly to try to understand reliability issue of each machine learning component in the way that we can actually build a system based on this individual component with a good level of reliability and trustworthiness. So a typical machine learning-based systems, it's composed of the following components. Right? So usually we move from the requirements we do for traditional systems, and then we have to build the architecture of the system. The architecture of the system is composed of a mix of AI-based components and non-AI-based components. The AI-based components are built using the data, which is the core, and nowadays we use a lot of frameworks to actually build the solutions that produce this component that we end up integrating in the system. And once this is done, we can deploy them in operation. So in the talk, I will focus on how the work we've been doing around the models and the component to improve the reliability of this component. I will also talk a bit about how when this component is integrated in the system alongside other non-machine learning components, how we do to detect out of distribution inputs to ensure that we're using the component in the operation environment in which it can be trustworthy. So many of you should have been seeing maybe this by now. So contrary to traditional system where we actually have the codes as the main artifact on which we're focusing alongside the other artifact to build the architecture of the system. In the case of machine learning systems, we have to deal with the data, which is the central artifact of the process, and then we have the model and the code. So all these three are important in the quality assurance process. Right? And contrary to what one may think in a typical machine learning-based systems, there are a lot of machine learning models interacting with each other. Right? If you see here the case of the autonomous driving system Apollo, this software has more than 20 machine learning models sharing information amongst each other, and sometimes some models are influencing other models. Right? So ensuring the quality, the trustworthiness of the whole systems, it goes beyond just looking at the individual algorithm of the different components. So now let's look at the pipeline that we go through when we produce a machine learning. So typically we start by configuring the environment in which we want to train the models. We collect the data from different sources, usually. And then we have to process this data. Once we have completed the processing phase, we have to decide how we want to learn information from the data. So we make architecture choices. We have to choose the architecture that we think most appropriate. And there is the hyperparameter space that we have to configure. Then we pick the activation function, the loss functions. We decide on what optimizers is more adequate for the process. And then only at that point, we start training the model. So there is a lot of design decisions that has to be made through this learning process. And then we can backpropagate, we train the model, we validate the model, and sometimes we have to tune the model, cross-process it before we can infer. This all to say that similar to traditional systems, this stage is producing a lot of statements. And these statements, like any software system, can be faulty, right? So these components fail, and they fail in different ways. Contrary, if we compare it to traditional software systems, the space of failures of machine learning-based system is much more broader because we have issues at the model level, right? So we can have non-optimal regularization that end up with under-specified model. We have implementation issues as we have for traditional system, and then we have a lot of data issues. So we have the data quality, it's important. We have been seeing works on looking at the smells in the data, noisy labels in the data, and so on. So there is much more to care in terms of quality assurance than we usually have to deal with for traditional software systems. And finding bugs in machine learning programs is usually notoriously hard. Right? So this is a statistic that has been produced in the literature a few years ago. What practitioners think, they consider that 80 to 90% of their time is spent debugging and tuning the model, like figuring the initial marks of how they want to learn. It's usually not the most difficult part of the process. And the reason why finding bugs in the machine learning code is difficult, it's because these bugs are usually, very often they are invisible. So if you look at this example on the figure in the slides, it's very hard to spot this just by trial and errors, right? Because the root cause of the problem here comes from the non-determinism of the functions. And then this flip in the label order result in unstable training process. Another source of difficulty of finding errors in this program is the fact that they are very sensitive to hyperparameters. So just the difference between a state-of-the-art model and a poorly performing model can be as simple as just picking the wrong learning rates for the model. So navigating this configuration space to ensure that the right parameters are picked and that all the errors catch can't be done by trial and errors. We need automated tools. So in my case, I think we need to be able to have mature quality assurance tools similar to what we have for traditional software systems to support the development of these components. This is an example of issues of bugs that you can say this is from a CLM. So just here, the sizing of the mapping it's not picked correctly. So during the training process, instead of extracting more and more features from the data, it's actually narrowing the scope. And this will result in a model that is performing poorly. You have a low accuracy, but you don't have a crash, you don't have a failure. So how do you diagnose for these kind of issues? So we need to have systematic process to be able to detect and correct these problems during the development of the system. So what we have done, so here I will show maybe a few work that we have done to support this. So we proposed the different tools. The first tool is a static analysis tool. So what we did is we brought program analysis to the problem. We propose a meta model of a deep learning, typical deep learning programs, and we specify different type of errors that occur frequently in this type of program, and we built a linter that allows to detect this issue pretty quickly. And it turned out that it's pretty effective. So we can actually support the development of this component in an efficient way as we do for traditional system. It's actually fast. But of course, a static analysis of this program cannot reveal all the issues because we're lacking the interaction with the data of the system. So the tool is available. I encourage everyone to try it out. It's open source, actually. So it's a bit of promotion for the tool. So you can try it. And how does the tool work? The tool has two key ingredients. So we have a meta model that we use to build a representation of the program that is trained to generate the model. And then we rely on a taxonomy of faults. So for different faults that frequently occur in those systems, we specify detection rules. And these detection rules are integrated in our tools. So whenever you have a program, you can actually use our set of parsers to create a model, a representation, abstract representation of your programs. And then once you have this abstract representation, you can use the tool to actually perform detections. So we do a series of checks based on the different type of errors that we specify in the tools. And then this way we can identify issues early on in the process and flag those issues and provide them to the machine learning engineers working to build the models. And this turned out to be very effective because this is fast. Of course, this cannot track all the problems. So we also propose a dynamic analysis techniques, which is a property base to catch errors during the training process. There is a strike overhead because we are actually extracting information from the training process as you train the programs. And based on the information extracted from the training process, we're making a set of verifications to detect issues that are actually occurring in the training program. So there is also a tool that we call the Deep Checker, which is a bit share a set of feature with AWS SageMaker, if some of you have tried the tools. And the tool is also pretty effective. So the evaluation is in the paper. You can see that the tool can actually detect even more issues than AWS SageMaker. And how does this work? Basically, we specify a set of properties that need to be maintained throughout the training process of your models. And as you train the models, we extract information and we perform verification. So we do checks and we detect deviation from what is expected to be the normal behavior of your model as you're training the model. So you can detect issues related to unstable parameter learnings, poor weight initializations. You can also detect activation issues when you have issues with your neuron. If you have dead neuron in your systems, you can actually detect this type of issues. You can also detect optimization related issues if you have a diverging loss, for example. This issue can be detected early on in the training process. So from the experiment that we have done in the tool, most of the issues are found in the early epochs of the training process. This way, although there is a bit of overhead because of the introspection of the training process and the additional computation that we do, this overhead is still reasonable and it saves the cost of going through all the training process before realizing that the process was flawed. So this automatic detection and debugging tools are actually effective to improve the reliability of the training process and the quality of the models that are produced. So the tool is also available for use. The way it works is that we're monitoring the training programs, and then we have hooks to extract information, pre and post conditions from the program, from the process. And based on the information, we perform the verifications, which are formal rules that we actually encode in the tools. And based on those verifications, we provide a signal to the user of the tool about issues that we are catching through the training process of the model. So the tool is available and it can be used. Are there any questions at this point in the talk? No? No question in the chat? No? No? Okay. So that's what that's some of
I will
the work
stop you
we
if
have.
there are questions.
Oh, there's a question?
No, I will stop you if there are questions.
Okay. So that's those two tools are part of the work that we've done on deep learning programs. And then there is also reinforcement learning programs, which is a different paradigm in the sense that it's mostly training an agent to explore an environment and acquire skills and be able to complete the task in a slightly different environment. And contrary to what one may think, this process is also very faulty very often. And the question is how you can ensure the quality of this process, how you detect errors in a reinforcement learning process, right? So we looked into this question and we did a series of work here. We talk about two works. The first one is we had to decide of what is a fault in a reinforcement process. What are the symptoms? How can we characterize the faults? And how can we identify the root cause of those faults? And once we had this taxonomy of faults, the second work that we did was to explore how we could actually provide testing supports, because we don't have input data and expected output data, so that we have an oracle in a typical sense. But then still, we want to have a mechanism allowing to reveal the manifestation of an error whenever it occurs in this system. So we propose a framework for mutation testing in the context of reinforcement learning. So I will also share this with you, hopefully to get your feedback on this. So to sum up, this is a broad view of how reinforcement learning works. So we have an agent interacting with an environment, and then we're providing him a signal that allows him to understand what we expect from him. So this way the agent learns the skills that is required to complete the task. So this is the lunar landing. It's a typical example for illustrating reinforcement learning. The goal here is to land this small spaceship within those limited boundaries. So in practice, usually developer will implement the whole process from scratch, or they will use frameworks. There are some generic frameworks like PyTorch or TensorFlow that provide the tool supports to implement reinforcement learning algorithm. Or they can also rely on more specialized frameworks like stable baselines that are more customized and tailored for the task. This simplifies the number of instructions they have to do, but it doesn't prevent them from implementing issues in this process. So this is an example of error found on Stack Overflow in a reinforcement learning process. So a reinforcement learning program can be faulty. In this case, the developer actually forgot to reverse the advantage during the learning process. And whenever there are errors in this case, it's result in a faulty agent. So the agent failed to acquire the skills for which it's been trained and failed to complete the task. So what we were looking in this context is how we can leverage software engineering approach to provide tool support for fault localizations or for testing of this typical type of program, where the goal is actually to acquire a skill for a specific task. There is a goal, but there's no oracle, no reference oracle from which to leverage the information to test the system. So the first thing we did in this work that was published at ASCG in 2021 was to try to understand what's the nature of reinforcement learning faults, right? To achieve this goal, we went exploring the repository of the most popular libraries that are used for building these systems. Typically, we look at the OpenAI libraries. We also look at the Keras and then TensorFlow libraries. We also look at what is being shared on Stack Overflow as feedback of people experiencing issues when building those programs. This allows us to collect the relevant artifacts. So we collect the artifacts, we examine the artifact, we label them to build a taxonomy of issues. And once we had the taxonomy of issues, we went back to the practitioners that are using the libraries from which we extract the information from the platform to validate the taxonomy. And once we had the taxonomy, we report the taxonomy. So typically we obtain different categories of faults that frequently occur in deep reinforcement learning programs. Some of them, there is an overlap between deep reinforcement learning programs and deep learning programs for certain aspects, because usually the neural network is used for learning policy. But they are deep reinforcement learning specific faults that occur only, that are related to the environment, to the agent, and to the interaction of the agent with the environment. So here you can see 11 common errors that occur, that we found occurring frequently in those programs. Some of them relate to the interaction with the environment, some relate to the explorations, some relate to the updating of the networks, and so on. So using this information, we decided to provide tool support to allow for early detection of these problems. Right? So similar to what we did for deep learning, we try to tackle the problem in 2 steps. First, provide a linter based on static analysis to allow for detecting the issues, just by processing the program that is being produced to train the agent. So we build a tool which allows to extract information from the program, relying on a meta model as well, and then we provide model-based detection for the issues. And this tool is also freely available, it can be used. But it's a static tool, so it doesn't allow to detect all the faults. There is everything that is related to the interaction with the environment and the action of the agent, we couldn't track this type of issues. That's why we had to go beyond a static view. So this is the meta model that we propose in the context of deep reinforcement learning detections. So this is based on DQN. So we use a graph transformation approach. We specify the structure of the programs and the constraints between the interactions, and we leverage this to actually perform the detection of issues whenever there is an issue occurring in the deep reinforcement learning program. But because this static views is not fully adequate for the type of problem that we're facing, we also explore the possibility of mutation testing for this context. So this is a recent work that has just been presented at ICSP this year. So we propose a framework for mutation testing in this context. But before we could reach there, we had a couple of questions that we had to answer, right? So what would be a mutant in the case of a reinforcement learning? What would be a Foutse? What would be a test case, right? So we had these different components to somehow define to apply to this context. So we needed mutations, we need a test case, we need a killing criteria in this case. So to mutate the agent, we look at 3 dimensions, right? So we could mutate the interactions with the environment. So we could add noise to the reward, for example, or repeating these observations of the agent. So this will be a type of failures that the agent could face. We could, at the agent level, we could fail, for example, to save terminal states, forgetting the discount factors. So this will be a problem that we found when we explore the taxonomy of faults. There are policy level issues, for example, changing activation of the policy network, it's a problem. So we leverage the taxonomy of fault that we produced in the previous work to design mutants for a reinforcement learning setting. And then the next question that we had was the test cases, because we don't have input and outputs that we can rely on to design test cases for this context. The only artifact that we had was the environment and the agent. So what we did is, the test cases are the environment. So we have to play with the configuration of the environment to try to uncover issues in the agent that is being trained, because the agent is trained to complete the task in the environment. So if there are changes in the environment that should preserve the behavior of the agent, but that falsify this behavior, then we have a signal that there is a problem with the training of the agent. So we have to play with the parameter of the agent. So if we go back to the example of the lunar lander, we have the gravity, the main power engine, the side engine powers. So we have different parameters of the environments that we can actually use to configure alternative environment to test the agents and detect whether or not the agent behaves appropriately or not. Now, there is a caveat with reinforcement learning in the sense that it's not expected that the agent will behave in a very different environment from the environment in which it has been trained. So we have to clearly identify the operation environment of the agent and make sure that we're testing the agent within the boundaries. Otherwise, we're testing out of distribution, and it's likely expected that the agent will fail the task, and then such tests will not be revealing any meaningful information about the behavior of the agent. So using the configuration of the environment, we actually generate different environments. And then we generate environments ensuring to ensure that the perturbation that we bring to the environment keeps the environment within the operational boundaries of the agent. The next item that we needed for mutation testing for reinforcement learning was the killing criteria, because this is a stochastic process. Usually, if you retrain the same agent multiple times, the agent will have a totally different behavior. So how do we detect an agent that is faulty from a clean agent just by looking at the behavior of the agent? What we finally use is to use statistical testing. So instead of looking at a single behavior, we look at the distributions, and then we try to catch agents that behave totally different from the other ranges of agents, a bit similar to what we have been proposed for deep learning in the deep learning context. So we repeat the experiment multiple times, and then we'll perform statistical testing. And it's only when the test fails with a significant effect that we actually detect a signal that the agent is being falsified. So to summarize a bit, we designed mutation operator by leveraging the taxonomy of faults. We designed test sets at environment instances that we use to detect buggy from healthy agents. And then we use statistical testing to actually detect deviation from the normal behavior for each agent. So using that framework, we can actually detect faults in the behavior of the agent. So if you look at this picture, for example, you can see that in the orange environments, the agent is being killed. It means the agent actually failed to learn the skills during the training process. While, for example, for the blue, the agent is not killing the agent in the sense that this variation of the environment maintains the skill of the agent. So the plasticity of the agent is being preserved. So parameter-based test environment generation seems to be a simple but effective way to get more testing environment and allow to perform testing for reinforcement learning, a bit similar to what we traditionally do for traditional programs. So we have been able in this work to kind of transfer what we already know how to do for traditional programs, but adapting the setting of reinforcement learning. And we think that this can even be used further for localization in terms of reinforcement learning. So this is some of the work that we've done for reinforcement learning agents. The whole method is automation is needed. So I think as a community, if we want to ensure that the development of AI-based component is trustworthy and robust, we need to provide a tool set that could allow for automatic and early detection of issues during the development process of this component, and eventually also propose repair techniques. So far we have been working on detections mostly, but we think that it should be possible to also propose repair mechanism to improve the behavior of the agent. So recently we have been exploring techniques for repairing neurons in a neural networks to improve the robustness of the systems in a continuous drifting environment. So there is possibility for leveraging what we know for program repair research to adapt to this type of system as well. So automated quality assurance is needed to support these systems. So this is part of the work that I wanted to share on ensuring the quality of the component itself. Now I want to briefly talk about what we have done on the integration parts. We mostly propose techniques for detecting out of distribution input data to ensure that the AI component is used on the data that is within distribution, which is where the model is most reliable, and that every information that is out of distribution is actually filtered out to a different component, mostly a symbolic component of the system. So this is an industry case study that we have done with one of the aerospace company in Montreal, so Bombardier. So in this context, the company it's using deep learning model to support the aircraft design. So traditionally, it's a simulation-based process. They have a high fidelity model that they use to simulate the behavior of the airplane and forecast the impact of every design changes that is made on the airplane on the property of on the airplane. What they wanted in this context was to build an AI-based surrogate, which is cheaper in the sense that it's much easier. It's more efficient to execute, at least at inference time. But this needed to be reliable in the sense that we need to have a good understanding of when the AI model is a reliable surrogate of the high fidelity model, and when they have to fall back to the high fidelity model and build this in the system, in the new software that they're using to simulate the plane. So this is an example of integration in somehow critical context of AI data-driven solutions with other more traditional components of the system. So here the goal was to train the model to simulate the design and forecast the impact of design decisions on the performance of the airplane, while maintaining the lead times and the development cost of the airplane. So we had to build a surrogate model for the high fidelity model, which is physics-based, and which has been used at the company for years. And we had to build this data-driven model. So the challenge in the process was not just to train the model, but was to detect the operating envelope of the model. So how do you identify when the model is reliable, when it's in distributions, from when you out of distribution, and how can we filter out automatically out of distribution entries or route them back to a different model? So that's the goal. That was the goal of this project. So what we did is, so there are different techniques that exist in the literature to try to detect out of distribution inputs. Some consist of training a generative model to mimic the distribution of the data, and then use this generative model to filter out new inputs that doesn't fit in the distribution. There are also uncertainty quantification techniques that are commonly used in the literature, but all of these techniques has challenges in the sense that, especially in the context of our problem, generative models were ineffective because they struggle with highly nonlinear complex input space. So we couldn't use this type of tools to actually detect out of distribution inputs. And also uncertainty quantification techniques usually degrade over time. When there are severe data shifts, the efficiency of those techniques tend to decay. So we had to come out with a new approach to achieve this out of distribution filtering that were more adapted for the problem that we were focusing on. So our solution was to leverage the smoothness property of the problems. So we had the physics models, because by training the model, we sample data and we fit the model with the data. And our intuition is that whenever we get a new data inputs, if the data is too far from the distribution that is used to train the model, the smoothness property of the data should probably decay over time. So we proceed by building profiles of each data point, and using this profile, we train a classifier to distinguish in-distribution data from out-of-distribution data. So we basically use this rule, and then we design a loss function that will be used to actually perform the computation. So we build point-wise sensitivity profile for each input data. You can look at the detail, but the details are mostly in the paper. But basically, for each input data, we build a profile of the data. And we use this profile for in-distribution and out-of-distribution to train a classifier to separate the two input data. So this is the full pipelines of the training process. So we label the data, we train the data, we use the new loss functions to actually optimize the process. And then we use this classifier to filter out the input and output data. So we test the accuracy of the classifiers, and then we use the classifier in production. So we assess the effectiveness of this technique on 3 models that were used in the company to predict different different properties: the time to climb, the balance field length of the plane, and the maximum takeoff weight of the plane. So we had 3 different models, and the use case of this model is whenever they make a change. So if they bend, for example, the wing of the planes, they want to know what will be the impact of these changes on the properties of the plane. So we apply the filtering techniques, out of distribution filtering technique that we had. We compare this with the Gaussian processes that they were using. And this approach is actually much more efficient for detecting out of distribution than the traditional techniques. And then we use this to optimize the cost benefits of simulating the planes. So using a new input, whenever we are in distribution, we will rely on the deep learning models. Whenever we detect out of distribution, we fall back to the high fidelity model. And then we use that to kind of predict the accuracy of the process and also the efficiency in terms of time of cost. Right. So the whole point of why I'm presenting this part of work, it's to showcase the challenges of understanding the operating envelope in the model to detect when the deep learning component can be used in a trustworthy way, and when the model is not trustworthy. And when the model is not trustworthy, in the case of our project, of our use cases, we were falling back to a high fidelity simulation model that was used, but that was more expensive to run for the company. So we found a trade-off. By combining the two in a hybrid setup, we could actually significantly reduce the cost while maintaining the reliability of the system. So you can see that we could decrease the error, and then we could also significantly decrease the runtime of the system. So by leveraging the a priori property of the systems, we actually increase the trustworthiness of the AI deployment component deploying in production. Okay. So roughly, ensuring the trustworthiness of machine learning system is challenging because contrary to traditional software system where we have to rely only on we have to cope with the code artifact. Here we have additional complexity that comes from the dependency of the data and then from the modeling process that generate additional issues that need to be detected. And our case is that we need to build automated tools to detect the issue early on in the process and allow for their correction, either by providing feedback to the developers or by supporting them with automatic detection techniques and repair techniques. The failing space of traditional system is much more smaller compared to machine learning-based systems, in the sense that for machine learning-based system, we have to deal with additionally with data issues, model issues, and implementation issues. But these issues can be detected effectively with automation approaches. And it's also possible to understand the operating envelope of the machine learning component when deploying them in production. And I will take any questions. I hope it's not too fast.
No, thank you very much, Foutse. So let's start with the audience. Any questions from the audience? Definitely testing ML components and some of these algorithms have different details that catch you. So from that perspective, we appreciate the insights you brought. If not, I'll start with a question. Okay. One of the things that we see in these systems is there is the software engineer skill sets and there's the data science skill sets. And when we have these different skill sets, and I think some of the techniques you talked about, I would not expect a traditional software engineer coming out of undergrad or even in the field would know. So what are some of the skills that are needed to be able to understand the defects that you're talking about, the faults, appreciate whether they are really a defect or whether it's normal behavior of the model development process, the algorithm process, and how do we teach these? Because I think we're now facing this turn within our field where there's the data scientists, there's the testers, there are different kinds of algorithmic levels of information that we need to be cautious of. In fact, our keynote yesterday said full stack developer maybe now includes algorithms as well. There's another layer in the algorithm. So,
and I totally agree. I completely agree, because all of the work that I've presented, we actually do this in close collaboration with colleagues also doing core machine learning research. For example, to detect errors during the training process of a deep neural network, you really need to understand, to clearly understand which property need to be present, the optimization process that is being performed during the learning process. To detect that there is an anomaly in the learning rate, you need to understand, you cannot use the algorithm as a black box, right? So it's important to understand how the algorithm works, and then what are the properties that are expected. But I think also on the machine learning part, there need to be more documentation as well about the techniques. So for a long time, it has been more in a trial and errors and task-specific approach, but more and more we're seeing a documentation of what are the common pitfalls, what are the common issues, why is this learning process working, why is it converging, what is it not converging, and what are the root causes of the problem. That's how we actually document the pitfalls that we detect in our deep check, right? So we first went and did a systematic review of everything that was reported about training deep neural networks, the properties that needs to be preserved, the common pitfalls, the common design configuration choices, like how do you pick the number of layers based on the type of data, how do you pick what is the best loss function, and so we documented it first, and then based on that process, we identified the property that had to be preserved and maintained, and that's how we build the verification routines. And the goal of our tool was to systematically, instead of, because the traditional approach was people were training and then they were observing the behavior of the model, and then they were going back and trying out different configurations and then observing the behavior of the model. We wanted to do it in a more systematic way, and then providing some kind of criteria for deciding whether or not this is progressing in a way that is expected, or this is progressing in a way that is unexpected, and then provide a signal for adjustment and maybe for recommendations. So that was the philosophy in those two tools. Right? So in that sense, I think a full stack, a software, we will have to deal with machine learning component. If not just integrating, but also retraining the component and ensuring that the retraining, for example, was successful, I think there needs to be an understanding of how the algorithm works in the first place.
Correct. And there are a couple other questions, but before I take them, I'll abuse the floor a little bit more. There's, I think, a difference from what I'm understanding based on your responses. There's a normal design process of the deep learning architectures, which you might consider as the defect or just a simply faulty way of developing it. And there's that, I think, balance that you need to provide, what these tools are able to detect that might be defects versus what are some of the potentially mistaken ways or false starts in developing the deep neural networks and the algorithms with that. So I think there's that trade-off that needs to be understood.
So they are the faults, and they are the bad practices. What we call like anti-pattern or design smells. They are the smells, they are not faulty. But maybe they result in more longer training regimes, but you still end up with a correct models. Maybe you have some slight inefficiency of the process, but they are not necessarily faults. But they are also issues that are really faulty. Then you are not learning anything from the data, for example. So those you want to detect early on, and you want to correct them to ensure that the training process works properly, especially when you deploy the models in productions. And then you have to retrain the model when the model is drifting, and then you have to continuously retrain the models. You need an automatic mechanism to do this in some sense. And that's why I think we need to provide tool support to actually ensure that engineers that are pushing this model and integrating them in the systems can get a diagnostic of what is happening, whether things are working well or not, even if they have to fall back to the data engineers, right, at some point.
Yep.
So that's a bit
there's that. Petra?
Yes. Yeah, thank you, Foutse, for your interesting presentation. And I totally agree with your message that we need more automated quality assurance tools. So it's good to hear that you are working on this. But in that respect, I was wondering, you presented some tools, some, let's say, point solutions for some quality assurance problems that can be detected or even repaired. But are you also planning to integrate them in some kind of quality assurance, let's say, platform or bigger framework?
Yeah, so the 3 of the tools that we build, we're actually integrating them in AWS so that people can use them. They are plugging actually for frameworks. Like, for example, if you're using TensorFlow, you can use our deep checker just within TensorFlow. We also build a tool for debugging reinforcement learning that is integrated in Hive. So if you're training your agent using Hive, you can actually just invoke our tool and then tag your training process. And the tool will allow you, basically what the tools does is that it extracts some information from the training process, perform some additional computation based on what we think should be monitored to detect potential issues and provide feedback as you're building creating the agents.
So your approach is your approach is to integrate your tools into already existing platforms. Yeah. Okay, thank you.
You can try them. The QR code, you can just scan the QR code and then you can try it.
Well, will we be? I'm assuming we'll be able to put up your slides, right? Share the slides with the attendees, and that's Jan, I think you have your hand up.
Yes, good. Thank you, Foutse, for really interesting work in this space. I really appreciate you sharing this with all of us this morning. The question I had was, my feeling is that most of your work is focusing on the training and validation of the machine learning or deep learning itself. And what I wanted to ask you is, what other challenges besides the training of the model itself can you or have you identified in your work? I mean, for instance, one of the things that I think is generally accepted within the AI community is that the amount and the reliability of the data that you use for training are a very important factor. So that's one. You already referred to the importance of having real-time monitoring in order to make sure that models basically do not go off the rails. So if we look outside of the pure model training itself, what other challenges do you see within the engineering of AI intensive systems that you think we as a community should really focus on and address?
So this is a very good question. Yeah. So I agree here.
Thank you. I try to ask good questions, you know. So
no, it's a very interesting question. Very good question. So this work was really focused on the algorithm and the training process, because at the time when we started looking at this, we realized that there were almost no tool supports. Like the process that we're seeing in our ecosystem were quite ad hoc. Like people were training, and then usually they just had this tensor board and to watch or weight and biases. They could get some signal from what's happening in the model, but they had a very partial views, and then the process were repetitive and so on and so on. So that's why we kind of try to provide this tool support to support them. But if we look at the whole engineering process of the AI systems, I think there are challenges even at the architecting of the system, right? Because as you can see here, is the models, they depend a lot on the data, and the data distribution is non-stationary, which means there's a lot of changes. So the AI component's behavior is typically very different from the other component of the systems, like in the sense that that component is likely to change more often. We need likely to have more observability of what is happening around that component in production. So this brings constraints on how we integrate this in the system, right? So what should be the ideal architecture of the AI-based system, in the sense that you can evolve that part at a different rate at the other part of the system. And also to detect things like drift in production, you need to be able to monitor what is happening, right? Yeah. So if you have logging, if you have to audit the AI component, how do you design the systems to allow you to be able to extract this information in a way that is efficient? Because if you extract too much information, then you can generate additional performance problems on the systems by monitoring one component. So there are challenges at the architectural level that I see it applying. Also, the requirement is also at the requirement phase. There are also challenges because not all the requirements of the system are explicit. A lot of things depend on what is in the data. And as the distribution of data will change, you're likely to have more or less what you used to have from that component. So how do you handle the space of the system to ensure that you can guarantee the quality of the service of the system in production and through the life cycle of the system? So I think those are also additional problems that I see.
Yeah, great. Sorry, I don't want to take too much of the time, and I know that there is another question. So, but thank you very much for your answer. That was very informative. Thanks.
Thank you for the really good question.
Justus?
Hey, Foutse, thank you for the talk. I was wondering actually for the linters and the automatic quality assurance tools. So how challenging is it to provide actionable guidance based on the findings? So I could imagine that for implementation errors and maybe also data issues, that it's fairly straightforward in some cases, but for model issues, how challenging or difficult is it?
So I think it depends on the issue. We have some work where we try to use the paradigm of anti-patterns to actually specify bad design practices for different type of networks, different type of models. And there is we catalog a set of issues to guide the design of those systems. And we build these issues by actually, was a bottom-up approach. So we pull what have been reported in the machine learning community for different architecture as good and bad practices. And then we try to reconcile the more common themes that were emerging, and then we specify them as bad practices to actually share knowledge, right? Provide actionable and guidelines on how you design. But this are usually very architecture specific. So let's say if you're doing graph neural network, the type of issues that you face is very different from the type of issue that you face when you deal with convolutional neural networks. But still, you can have this type of guidelines documented and provided to users. They are different from errors. So those are not errors, but they are recommended and non-recommended practices that emerge in that community. So there we have done some work on documenting this, and I also know some other teams that are working on documenting more of these patterns and anti-patterns to support the development of these AI-based components. So I think it will take a mix of automatic tools for detecting errors and also at the architecture levels, right? So you can imagine if you, with this design smells that we specify, you can imagine that you can perform refactoring supports, for example. You could perform refactoring to improve the component, the design of your neural network, or the design of your graph neural network. It depends when it gets more complex. That's why you need tool supports. And then also some of those guidelines depend also on the structure of the data that is used to train. So there is this interaction between the two that needs to be taken into account within the guidelines. So the guidelines usually provide you hints of how to design it if you are in a context using this type of data with this type of regime and so on. So that there are efforts that I'm seeing exploring, coming more and more in that direction. And we also we have a paper that we produced on this 1 year ago, but I also know other people are documenting more on that. But still, they are very architecture specific.
Understood. Thank you.
Foutse, I want to take it back to the question that Jan was asking. And your tools and test suites are focused on the model development stage. But there's also an aspect of this, once the model is integrated into the system, some of the defects might in fact appear at that time. So how transferable are your tools to that system integration and system development part of it? And or are they just solely focused on model development? Once the model is developed and transferred to the software engineering team or integrated into the system, are we talking about different test suites and different kinds of defects?
So So some of the tools that we propose also test the trained model. So we have tools to generate test data to actually try. Those are robustness testing based tools. Roughly, the idea in those tools usually we use search-based approach to explore the input space of the model, to reveal corner cases, issues, and so on. But still, we are at the model component. And then once the model itself and interacting with the other part of the systems, there are other tools that are sometimes proposed to test that the inputs that are fit to the models are equivalent to the input that we use to train the model. So those are different set of tools. And then you have integration testing that has to happen. We haven't produced much integration testing tools, but I think some of the existing tools that we're using in production for integration testing could still be valid, because at the end, once the model is trained, the model is just, it's freeze, right? It's just processing information, and then it's sending the information to the other components. So I think we can use existing integration testing tools that to actually test for errors or issues at that point, and maybe come back to training.
It's, I guess, from going back to your taxonomy, the question being, are there any defects that you wouldn't be able to catch during the development time, even if you had the tools and the formalisms, and it becomes apparent latent, but now once you know it, you could bring it back to the model development stage and then augment that? Have you come across examples of such defects in your way or faults?
So one thing I could say is, if in production you have, because some models are feeding other models, which means in these interactions with this hidden feedback loop, you can actually have defects occurring in production from this process. And if you detect, so you will need a different set of tools to actually detect these issues, in my opinion. But once you detect, then you can come back at the training process, and even at the architecture, decide on how you want the component of the models to be interacting with each other. What kind of features you want to rely on, or which feature maybe to exclude to avoid this feedback within them. Because you may end up, you have some system where you end up having your model being influenced by its own output through a process, because it's feeding another model, and then you're relying on some output to make your decision in your model. I think those type of issues can emerge in production as well. And then
there's a feedback loop between the system and maybe information to be learned, which could influence the defect analysis process and enhance the tools as they evolve.
Exactly. And we need tool support to detect for this. We haven't produced any for this, and I haven't seen much yet from the literature. So I think in the community, there are many problems that we have to be tackling within that interaction between those components in production, in my opinion. And especially because the data is drifting in production usually, which means the quality of the AI component is constantly, is not stationary, it's changing as well. So their behavior is slightly changing.
Yep, that's true. Tenzin?
Hi, thanks for your talk. Very interesting. I work in the aviation safety community, and there's a growing interest in use of machine learning in many different aspects of the aviation industry. I'm just wondering where you see sort of the automated quality assurance tools that you've worked on, or perhaps any future gaps in terms of supporting sort of certifiability or safety of machine learning systems for these sort of more safety critical applications, if you have any thoughts on that.
I think for certifiability, we are still very, very far from it. So this project that I presented, the last piece of my talk, it's within the context of, we have a project that we call DEAL, for the Dependable and Explainable AI. The goal of that project is actually certifiability in the aerospace industry. And although we're making progress, we're still very far from the standard of what you can certify, right? Because the requirement for certifiability is that you should be able to ensure full transparency, right, throughout the process. And we're actually even struggling with explainability at this point. We don't have any good techniques to explain exactly the decision process of the model. The best we're able to do is actually being able to detect the operating envelope of the model, so that whenever we're out of distributions, we fall back to other components, and we're trying to guarantee that our out-of-distribution detector is reliable enough so that we can rely on it to make the switch between the old component and the machine learning component and so on. But still, that is not certification standard quality level. We have more robustness guarantee that we provide on the process, but certification is still a very long shot. I know there is a lot of excitement in and push in the aerospace community because most of the techniques that they are using are very expensive. Like simulation-based approaches are very, very expensive. And in many cases, we can get decent performance with data-driven models, but decent enough, not reliable enough to replace fully the simulations. So that's why we're playing with this hybrid trade-off within.
Yeah, thank you. Very interesting.
Okay. Thank you very much. I think we don't have any other questions. We very much appreciate Foutse bringing us the component reliability and trust perspective and answering the questions. And we'll have you back at the panel session as well, and we'll have opportunity to discuss further. If there are no other further questions, I will close this session. We'll come back at 6:30. My colleagues and Cheng will be chairing, and we'll continue with the paper discussions. Going once, going twice.
Thank you.
Thank you very much. Thanks a lot, Foutse. We really appreciate your making the time. All right.
Absolutely. Thanks a lot, Foutse. Wonderful. Here's your applause.
We'll be back at 6:30.